All right, let's take a look at the homework problems here, questions you had. Now, okay, let's go ahead and get started. Quiz probably Tuesday, and remember one of the things I was talking about here, kind of two tracks of problems, two kind of things going on here that will be focused on the quiz. It's a pretty important quiz. I mean, as I've talked with a few of you about grades and so forth, you know, we got the end of the term coming up here, coming up fairly quickly here, and we'll have a couple of different grading opportunities. This quiz will be at least one more quiz, possibly even another shorter one at the end. We will not have a term test at the end because, as I think I told you at the beginning of the year, I consider this course really 3 terms long, and so we'll have one at kind of the halfway point, kind of a term and a half in February. That'll be our midterm test, and then we'll have our final later on. So there'll be this quiz, at least one more quiz, and possibly another one. There'll be another homework grade. There will be an extra credit opportunity at the end of the semester. The last day before Christmas, we traditionally allow students to perform some sort of calculus carol for extra credit. Now, if you're doing it, yeah, you know, it's extra credit, but it's not that much extra credit. I mean, in other words, if you're at a C and think, hey, this will be the thing to get me to an A, that ain't going to happen. But it might be something that it'd be worth a few points. If you're on that bubble between a C plus and a B minus, or something like that. So if it's 6 points of extra credit or something, in the grand scheme of things, it might adjust your grade a point or two. But it's at the most, I would think. So it's as much for fun as it is for anything else. But it is an opportunity. So if you are in that kind of that borderline at that point, it sure be worth looking into. But and what it is you can do it alone, and of course doing it solo is worth a little more than doing it in a group. But you can do it as a group, and typically the rules are just take some traditional Christmas carol. If you can't sing a Christmas poem or something, and rewrite the words having something to do with calculus. Okay? And I've videotaped them every year, and I'll show you as we get closer. I'll show you some videotapes of other years. Now, I won't, so you will be videotaped, but I wouldn't have to. Yeah, I won't put it on YouTube. The only people that would see it would be maybe another year's class or something. But usually I just kind of pick out the greatest hits for those. So anyway, now I do ask that it be original. Now you can get some ideas. I mean, obviously there's ones out on YouTube. It's not. I mean, I've been doing it for a long time, but there's a lot of other people that do it here lately. Now with YouTube and everything, there's a lot more access to it. But try to make it original. You can get some ideas from those sources, but if it has something to do more with our classes, it makes it better. So anyway, that's out there at the end. But otherwise, that's about what we have left for grades, and so we need to get focused in here these last 3 weeks and try to do a good job. So. Let's start on page 129, talking about the differential equation ones here. We worked number 6 yesterday. Our main focus on the differential equation yesterday was this idea of verifying something was a solution, right? We had 3 types of differential equations, the types we can easily solve, the one we memorized, this one here, the exponential function, And then there are those that the best we can do is just verify that something is a solution. Okay? So anything on the first section? I didn't see too much on the what you had said about this first section, but maybe I missed some. 17 maybe? Is that anybody like to see 17 on this one? Okay. So all right, it says show that y equals x cubed. Show that y equals x cubed is a solution to this differential equation. Xy prime equals 3y. Okay? So let's, here's what I showed you yesterday. Is anytime it says show that it's a solution or verify that it's a solution, kind of this T-chart or whatever, however you want to call it. That's, not that you have to do it that way, but I'm just saying it needs to be pretty clear. Okay, your work needs to be pretty clear that you're showing that it is a solution. And sometimes people have a question, well, how do I know where to put the T-chart? Why do you put it there, why not over there? Remember, this is the proposed solution right here. Think back to your algebra equations. If I tell you 2 is a solution, that's the thing you plug into the other equation. So this is the thing, this is the solution. The solution gets plugged in to the other thing. So this is the one that it gets plugged into. All right, so in place of the y over here, I would put an x cubed. The x I would keep there, and in place of the y prime, I would do this derivative over here. This derivative would be 3x squared. So right here, I would put 3x squared. I work that out. That's 3x cubed. On this side is 3x cubed. And that is it. That work shows that that is a solution. So y equals x cubed is a solution to that differential equation. That's what that looks like. Okay, now sometimes the algebra is more difficult. Sometimes the derivative you have to do is more difficult. But that's basically how a show or verify or prove that something's a solution to a differential equation. That's how it works. Okay? So most of those were that way. 19, 20, 25, those all were pretty much that same sort of a problem. Okay? Let's take a look at 2.6 then. Looked like there were a number of people that had problems there. Now, (2.6) is when we got into the exponential functions and log functions, and that is our special memorized differential equation. So section 2.6 is where we're going to really work with this one. All right, now remember I said yesterday that the other track of problems we do are the max-min problems. We've got our differential equation problems as one track, and we've got our max-min problems as another track. Well, the sine and cosine section is mostly going to be about the max-min problems, because those lend themselves nicely to that. Exponentials and logs, not so much. They don't really have maxes and mins very often. So that's the section we do a lot with the other track. We're dealing with these differential equations. And so that's what 37 and 38 and those were about. Well, actually more so 47. But let's just go through. These would be worthwhile questions here. 37 would be on kind of that max-min track a little bit, in the sense that it's not really talking about differential equation, but it is talking about this velocity, position, velocity, acceleration, which is kind of a derivative. You know, sometimes we get into maxes and mins and inflection points with those a little bit too. All right, so let's talk about that. You've got this function x of t equals natural log t, and you know, so not only do we have these new things we're learning, differential equations, and then using the max-min stuff, but we also have to be able to, as we learn these new functions, these new derivatives, we got to be able to go back and answer some of the old questions we've had in the past. And this one is kind of, that's why I threw this in here. Find the average velocity. Well, this is the function for the position of the particle. all right, on the x-axis. Notice something that's a little different about it is it's the function x actually is our output. A little bit unusual. X is the output here. T is the input. This is time. So we've got a particle moving back and forth on the x-axis. Wherever it is on the x-axis is its output. And the time it's there is its input. Okay? How do we find the average velocity? No. The temptation is to think velocity is derivative. That's right. And so average, you'd maybe add up and divide or something like that, but that's not what we want. The key is instantaneous rate of change versus average rate of change. Average rate of change is slow between 2 points. So the average velocity, I would be extremely happy if everybody on their paper had this right here for 37A, because this is what you should have. When you hear average in this class, I can't think of a time when we do what you normally think of when you hear average, which is add up and divide by how many you have. We don't do that. For us, it's average rate of change. An average rate of change, in this case, it's rate of change. Remember, velocity is the rate of change of position. So when they want average rate of change or average velocity, they're asking for average rate of change of x, which would be this. So all we're doing is substituting in an e in to the function, like so. What's ln e? 1. ln 1? 0. Those are 2 values of natural log we have to have memorized. This would be a no calculator problem. ln e is 1. ln 1 is 0. This answer is 1 over e minus 1. Now, if they gave us units, which they did, then we should put the units, and that would be meters per second. And that's how we would leave our answer. It's a no calculator problem, so I wouldn't expect you to simplify any more than that. Okay, that was part A. Part B says, find the instantaneous velocity. What's that, Aaron? Instantaneous velocity. That's the derivative, right? That's the derivative. So position x, x prime would be the velocity. So what they're asking for in that problem is x prime of e. But before you can find x prime of e, you need x prime of t, right? Before I have some place to plug e into, I have to find the x prime equation. So x prime of t, if this is x of t, what's x prime of t? 1 over t. That's the rule for the derivative, right? The derivative of natural log of x is 1 over x. Well, natural log of t is 1 over t. So that's the derivative. That's the instantaneous velocity. So at point E, it'll be 1 over E meters per second. That's 37B. Average rate of change is slope between 2 points. Instantaneous rate of change is the derivative. We now have these derivative formulas, and we can plug in and use them. What's the instantaneous acceleration of the particle at 2? What's acceleration? The second derivative, x double prime. So we need x double prime of t. So x prime of t would best be written t to the negative 1. So we'll do a power rule on that. Negative 1 t to the negative 2, which might be helpful to write as negative 1 over t squared, since I'm now going to plug in a, what they say, a 2. So I'm going to plug a 2 into that, and so that'll be negative 1/4 meters per second squared would be the acceleration at time 2. So we've learned these new derivative rules, and now we want to be able to use them in some scenarios. And some of those scenarios are based on things we've learned in the past, right? We've already done this position velocity acceleration relationship with f prime, f double prime. In this case, x prime, x double prime. Okay? And that's all there is to those. All right, number 47. how you write this stuff is important. Writing out the function and so forth is very helpful. All right, 47 says First National Bank advertises 8% interest compounded continuously. P of t denotes the value in dollars after t years. Then P prime equals 0.08p. So my hope is as soon as you read that right there, you thought of type number 2 on the differential equations list yesterday. Type number 2 was y prime equals ky. That differential equation has this as its solution. Okay? So it's guaranteed next Tuesday there's going to be a question, something like this with money or some exponential growth or something, because it's such an important differential equation. All right? When you see that, you immediately write its solution, P equals AE to the KT. Right? We're using P in the problem instead of Y. Okay? But hopefully you can look at this and see that those two are the same thing. Now, actually, I did something wrong there. What did I do wrong in my solution? It's just the E. That's a good question. It's just the E that's raised to the KT. The A is multiplied outside it. But what did I forget there? K. What is K? In this problem, the K, the number in front, this K right here is that K right there. Okay, so I should have put the 0.08. I should have put the 0.08 in there. Okay? But the A is a constant. The A is some constant that we don't know. But this is where that initial condition comes in. They then told us that at the beginning, or now, we're going to deposit $2,000. So what does that allow me to plug in here? 2,000 where? Well, we got to be careful. It turns out that 2,000 will be the A, but only for a very specific reason. So I want to avoid putting the 2,000 in for the A right this second. You'll see why in a minute. But when they told me that we deposit 2,000 now, what I would like you to start to do is think in function notation here. P is the dollars deposited at t years. So if I deposit 2,000 now, how would I write that in function notation? P of 0 equals 2,000. That's what they just gave me. But in that sentence, they gave me that value right there, which means at time 0, P is 2,000. So I get e to the 0.08, and then I put a 0 in for t. Now, as it turns out, 0.08 times 0 is 0, e to the 0 is 1, so we get A equals 2,000. In the old PERT formula, or so forth, anytime you put a 0 up here, then this A will be that initial value, but only if you start at time 0. Okay? So A does equal 2,000, so I'm going to rewrite my formula then with the 2,000 in there, e to the 0.08t. Now I've gotten rid of all of the unknown constants, and all I have left is my input variable t and my output variable p. That's what we want to do. So we went from our general solution here that we've memorized. We took our initial condition, put that in, found the unknown constant. We now have an equation to work with. Then we can answer the question. How much will it be worth in 10 years? What do I do?
Multiply.
And what would I call that in function notation? P of 10. So what I'm finding at this point is P of 10, which means I want to plug a 10 in. Not that you have to write that P of 10 there on your work like on the quiz, but it certainly is helpful because, number one, if you wrote that and made some mistake, it might be worth a point in the sense that, okay, this person's showing what they're thinking, what they're going to do, and they know what needs to happen. They just may fail in the execution. Okay? So putting stuff on paper is always best. All right? And the better you could get at kind of showing this notation and writing this out, you'll find out as we get into more complex stuff that If you write the notation carefully, and if you write it well, it can help avoid confusion in some of these problems. Okay, and so you go ahead and you work that out, and what's it come out to? Okay, 4,000 something. Okay, whatever. And in a problem like that, you would not need to go to 3 decimal places. If it's a dollars problem, it may say to the nearest dollar. If it doesn't, just go to the nearest cent, you know, and round it in 2 decimal places is fine. Okay? All right, but that's a pretty typical differential equation type problem. You're given the differential equation, you either solve if it's type 1, or if it's this memorized one, we just write it down because we recognize it. Or if it's type 3, which we're going to work on today, they'll have to give you the solution. They'll have to have given you the solution. They may ask you to verify it, but they'll have to give you the solution, and then you can work with it from there. All right, let's go over to section 2.7. All right. $39 and $44. Now, this one looked a little iffy on some papers. I'm giving you the odd ones here with the idea in mind you can check your answers easily. This is one of those that should have a lot of you should have number lines, okay? You should have list of candidates, you know, all of this stuff. Now we're looking at the interval 0 to 2 pi. Now we're on that other track of problems, the one that deals with local max min and so forth. I told you on these problems you do not have to draw the graph, okay? But we're going to do local max min, global max min, points of inflection, all that stuff. So where do we start? Derivative, set it equal to 0. And since I need inflection points, I'm going to need the second derivative also, set equal to 0, because that's where we look for inflection points. Those are local max mins of f prime, which means when f prime changes, f double prime changes from positive to negative. So the first derivative is what? 3/2 plus cosine x equals 0. All right, let's go ahead and solve that. Cosine x equals negative 3/2. When does cosine x equal negative 3/2? Never. Right? Because that's negative 1.5. And cosine and sine can only have outputs as big as 1 or as little as negative 1. Cosine will never equal negative 3/2. So there are no stationary points. So what's that tell me about local max and min? No local max and mins. Okay, what about global max and mins? Has to be at the endpoints, right? Now how am I going to show which is which? Okay, one way would be do my list of candidates still, right? So remember we talked about, we haven't done this for a couple days. One way to do global max min is do list of candidates. Okay? So if I want to do, for my global max min, I want to do a list of candidates, where do I plug those candidates into? See, we got to really be careful here because when I do an H prime number line, I plug into H prime. I want to see if H prime is positive or negative. See if the graph's increasing or decreasing. When I do a list of candidates, what am I looking for? I'm looking for the biggest and smallest H values, right? Y values. So I've got to plug it into the original function when I do a list of candidates, right? We do a lot of things where we plug into these different functions, but we got to know which one to plug into, and we got to. The reason we know that is what does it tell us? H prime tells us when the graphs, if H prime is positive, it tells us when the graph's going up and down. We do that for local max and min. But if I want to know their values, I've got to plug in to the original. So I need H of 0 and H of 2 pi. And that's fine. I got two candidates, so that's fine. The littlest one will be the min. The biggest one will be the max. So I put a 0 into here. What do I get? 0. Put a 2 pi into there. What I get 3 halves times 2 pi plus sine of 2 pi, which is 0. So what's that, 3 pi? Right? 9 something. So that's clearly the max. Usually we only care about the output value. I think in this problem they did ask for both coordinates, so I guess you could circle the whole thing. That would be both coordinates. So your global max is 3 pi, your global min is 0. Now, also, Jacob, I don't know, maybe you were saying that. What is h prime here? This happens to be a pretty easy h prime right here. What would the graph of that look like? Shift it up 1.5. Well, what happens if you take cosine, shift it 1.5? It's completely above the x-axis, isn't it? Because the cosine goes down -1, and so you shift it up 1.5. This is completely above the x-axis, which means h prime is always positive. So I wouldn't have had to do a list of candidates. I could have said, since h prime is always positive, h is always increasing. If h is always increasing, the minimum would be back at 0, the maximum would be at 2 pi. Now, you still had to plug those in and give the maximum values, so the list of candidates probably would have been shorter anyway, because you still needed to get those values. Okay? But that's a way we could have answered that. All right, we still need the inflection points. Those happen when h double prime is 0. What's the derivative of h prime here? Negative sine x equals 0. We can solve that when sine x equals 0, which is in our interval really just at pi. Because we usually don't use the endpoints as our local max and mins. I mean, we still use them as stationary points, but we don't use them for local max and mins because we don't look outside the interval. Okay? So I'm just going to use pi. And that's a possible inflection point. Okay, that's not enough. We need to put it on a number line. So we have h double prime. We put pi on the number line. Pick something over here like negative pi halves, and I know that wouldn't do it. It's positive pi halves, and then 3 pi halves. Okay, and we've got to put those into the second derivative. So pi halves. What's sine of pi halves? Sine of pi halves is 1 with a negative on it. 3 pi halves, sine is -1 with a negative on it, makes it positive. So I do have a change in concavity. Think about the chart. H double prime changes negative to positive. So I would need to say inflection point at x equals pi, and the reason H double prime goes negative to positive, so H changes or goes concave down to concave up. Now I could have just said H double prime changes sign, because it doesn't matter if it changes concave down to concave up or vice versa. To be an inflection point, we just have to have a change in concavity. So H double prime just has to have a change in sign, so that would have been enough. But you've got to say that. Okay? Local max min, you've got to say, anytime we're switching columns, we've got to make that sentence there. If local max min, change from positive to negative, vice versa, or inflection point, when H double prime changes positive to negative. We've got to make that connection right there when we justify it. Okay? So that's 39. All right, let's go to 44. Now, I failed to tell you yesterday. I figured after I realized that you probably would do this anyway, and that is use a calculator on this one. You know, now hopefully you tried to solve it without a calculator and you know, got to a certain point and kind of got stuck. Well, let's look at it. So I need a volunteer. Go ahead and get on the calculator screen, please. And let's type in that function for number 44. Let's do let's do this. Let's do it this way. Go on the home screen, or on the calculator screen, and type in define. Define, and let's define f of x as that function. Because we get into one of these problems where we're going to be doing derivatives and second derivatives, you can really shortcut your work, and we're going to be plugging numbers in to those things. You can really help yourself if you define them. It can actually save you some time in the long run. Okay, looks like we got about 4 people doing it. Come on now, let's get logged in here. Everybody ought to take a crack at this. Okay, let's type define f of x equals Jake, you're not logged in. What's the matter? What's that? Your calculator's dead. Oh. All right, Harry, you're the presenter.
Wow.
Okay? All right. Need a little levity today, so it's always good. Always good for something. All right. So we've got that defined. All right. So now we read through the questions. It talks about stationary points. Where is f decreasing? Find the max and min values. Okay. Questions A, B, and C were for all of those. We're going to need what? Derivative solved equal to 0, right? So go ahead, Harry, and everybody else in here, go ahead and do the derivative. Grab your, get the derivative template there. Because there will be a calculator, there will be, one of each type in the quiz next week, calculator and no calculator. So we go ahead and do the derivative of f of x, and there it is. And while we're at it, might as well do the second derivative. Now you got 2 choices. You can either do the derivative of the one you just did, or you can grab that one next to it, the one that's got the 2's on it, and you can do it just like that. Do the second derivative of f of x. Okay, so now we've got those, so we can always go up and grab them if we need to. Okay? All right, so let's go ahead and do the derivative and set it equal to 0. So let's do a solve. Okay, and we're going to take the derivative, set it equal to 0. We have to type comma x. And what is our interval here? See, he's got negative 97 as an option, right? But we have an interval here that we're limited to, and that's what? 0 to pi. Is it 2 pi or? It's just 0 to pi. So go ahead and go up to that solve. Let's do it again. Let's limit ourselves. This is yesterday we said this is where we do the vertical bar out at the far end. Put the vertical bar, and then we do 0 less than or equal to x less than or equal to pi. Okay, so that keeps x between 0 and pi. All right. So our stationary points, oops. Okay, read those. Oh, I guess I didn't need to erase that. So, stationary points where f prime was 0 on the calculator, what were they? Read them to me.
0.524 and 2.618.
2.618. All right, just do it. So, and that's what your work will look like on a calculator problem. You would write down, and actually, I would have f prime written out. Okay, you should have f prime written out. All right, what was f prime, Harry? What was the f prime function?
2 cosine of 2x minus 2 sine of x.
Okay, so you should have f prime written out, set equal to 0. Then you can go right to your calculator to solve it. I don't even care that you use the calculator to do the derivative. Now, to be honest, let's go back and take a look at his calculator again. I'm perfectly fine. Scroll up here. I'm perfectly fine if you do the derivative on the calculator, but let's make sure we understand why, because I am going to ask you some derivative questions on the no calculator part. The derivative of cosine, of course, is negative sine, so we can see where the negative 2 sine came from. The 2 just hangs out there. And yesterday we said what happens with this 2 on the inside?
Kicks out.
Kicks out, because it compresses a graph which stretches the slopes. So the derivative of sine 2x is going to be cosine 2x, but it also has to kick out a 2. And so that's why it is what it is then. So understand that, because we have to be able to do that. But if it's a calculator problem, go ahead and have the calculator do the derivative. That's fine, just if you want to double check yourself. Sometimes it's just as fast to not, but it's up to you.
How come they're flipped?
I think the calculator is just programmed to try to put a positive. If there's a positive term and a negative term, it'll write the positive one first. But it doesn't matter. I mean, it's the same thing. It's like 4 plus 2x. We normally write 2x plus 4. They're the same. All right. So you always have to give your answers to 3 decimal places. So when it says, are there any stationary points? If so, where? Here they are. So these are our stationary points. That's our answer to part A. So we have to have 3 decimal places. But later, if we would use these in a calculation, which we will, you would want to come grab the, or use about 6 or 7 decimal places on those. Okay, we'll do those here in a second. So part B says, where is f decreasing? So what would we need to show for that? We need a number line. Okay? We would need a number line. We don't want to go, I mean, I suppose you could go on the graph screen and draw a graph of f, try to see where it's decreasing, then you got to find where the max is, and then I want to see more than that. You've got to show something using these values. So the number line would be the thing to do. Label it f prime, put these 2 numbers on there. Again, whether you put a couple decimal places or whatever on your number line doesn't really matter. Okay? Now we need to pick some number in between these. Since you're using your calculator, it doesn't really matter. 0, 1, 3, those are fine. And we need to plug those where? Into, okay, for the video here, I'll just make sure. Okay, so I'm going to do a number line like so with my stationary points. I need to plug those back into f prime. Okay, so an easy way to do that is to, okay, he's already highlighted it, arrow up and highlight your f prime, and grab that and bring it down, and then what? What's a good way to substitute though? With the vertical bar. The vertical bar is a great thing to use here. Go outside at the far end and then put x equals what? What's the first one we want to put in?
0.
We want to put in 0. This is a great way. Now, see, I never defined this as anything. So I didn't define the derivative as anything. Otherwise, if I defined it as g, I could put g of 0 right now. But it's probably just as fast to do this. Okay? So now I put in a 0. So see what we just did there? We just put a 0 into f prime, and we got out a positive. So I go to my number line, I put that. And now it's really easy to just go up and grab it to plug in a 1. All you have to do, go up and grab it, hit enter, change a 0 to a 1. Yeah, and then it gives you this. So you go ahead and hit control enter, so you get a decimal. And there you can see it came out negative. Okay? So I'm just putting these on my number line now. Okay? And then we go in and we put in a 3, and it came out positive. Right? So we're doing the same thing we had been doing, no calculator, but now we're just using our calculator to find those values. Okay? So the answer, where is it decreasing? It is decreasing from 0.524 to 2.618. Same kind of question we did on that Chapter 1 quiz with the graphs. Now we're doing it with the equations. Okay? Part C, find the max and min values. All right, whenever it asks it that way, which max and min are they talking about? Global. That is, they're talking here about global max min. So, that's your list of candidates, right? That's list of candidates is what we want to do there. So, list of candidates, we plug those back into what? The original function, because we want to know the highest and lowest values of f. So we're going to have f of 0, we're going to have f of pi, we're going to have f of 0.524, and we're going to have f of 2.618. Now, since we did define our original function as f, and that was why I wanted to do that, because I knew that I may be plugging into that later. See, if I would have started here by just doing the derivative on my calculator, then I would not have had f in there anywhere other than inside that derivative calculation. But now all we have to do is type f of 0 and hit enter. Okay, f of pi. Probably going to hit Control Enter most of the time when you're doing the calculator, because you really want the decimal versions most of the time. Okay, -2. And of course, if you type in a decimal, now don't stop at 0.524. Okay, it's very important here. Now, on this one, this is where we're going to actually give a max value. Now, we'll see if it would have made a difference. So here you can just write down on your paper 523, 598.
You can just hit enter and then delete it.
Yeah, you can hit enter and just delete them all. That's fine. Delete a whole bunch of those.
What?
Escape. Just hit escape. Anytime you have a cancel, you hit escape. Okay. All right, so now do F. Okay. What was it? 523, 598, I think. Okay. Go ahead and hit enter. Now, to 3 decimal places, that's 2.598. Now, try it again, Harry, with just 0.524 typed in. It's possible that you get away with it, you know, and you really do out to about the 5th decimal place. But it certainly isn't something you want to rely on. Using rounded values with 3 decimal places and hoping to get an accurate answer to 3 doesn't usually happen. The safe bet is go about 6. Okay? All right, and then finally the last one, -2.598, and there is some symmetry to these, which kind of makes sense with sine and cosine, and that might be true, but all right, so find the, and again, answer the questions. Find the max and min values over the interval. So the min value, we want to circle that. The max value, I don't want to circle the other part of it. I don't care. It didn't ask about the endpoints, and don't give that extra information. The min value is this. The max value is that. Okay, D, where is F concave up? What are we going to do for that? Second derivative. So we need to do the second derivative. So let's go back to the screen. And I should show this for those watching at home. Okay, so there's our list of candidates right here. Okay, there's our answers. Okay, now we're going to do the second derivative. All right, and the second, go back, what was that? Okay, no, stay right there. -4 sine 2x. You should write this on your paper. Okay, anytime you use your calculator to solve an equation, that equation needs to be written on your paper. So the second derivative is that. We're going to set it equal to 0 to get our possible inflection points. Again, they didn't ask for inflection points, but the number line is what's going to tell us when it's concave up or down. So we need to find our possible inflection points and do our number line. All right, so go ahead and solve that. If you just close the, there you go, yeah, just close that right parenthesis and then it works for you. Comma x, and we're going to have to do the vertical bar again. At the end, we're going to have to tell it we want to solve this between 0 and pi. Okay? Okay, does that number look familiar at all? That's pi half, right? That's pi half. Okay? But which is you're here or there. I mean, it doesn't matter if you recognize that or not. But that's what it is. But there's our possible inflection point. Okay? We're going to make a number line. Label it F double prime. We're going to put 1.571 on it. Just pick a couple numbers on either side, 1 or 2. We don't need to use pi type values on these because we're using the calculator here, so we can plug in anything. Okay, so go ahead, Harry, plug in a 1. So we got an arrow up there. Find that second derivative. Okay. Again, this is the vertical bars are really good. You use it on the solve when you restrict the domain, and you also use it when you want to plug a value into a function that you already have written up on your calculator screen.
Do I have to solve on this?
No. Just this is right. Just vertical bar, and then put x equals 1. Just you don't have to grab it again. Just hit control. You can just hit Control Enter again. And yeah, if you forget, just hit Control Enter, or always take the last thing you did and do it again.
Nice.
Okay? So what's that, negative? All right, and then try it with a 2. Oops. And we get a positive. Okay, so the question was, where is F concave up? We have an interval, though. So we want to say 1.571 to pi. Okay, we are in an interval from 0 to pi. And I know it's a closed interval. You do not need to close this. Any questions asked, where is it increasing, where is it decreasing, where is it concave up, where is it concave down? We usually put open intervals for those questions. Okay, so it's concave up here where F double prime is positive. All right, that's a pretty good review of that one track with the local max min, global. We've done some global max min with listed candidates. We've done some concave up, some inflection point stuff. I mean, it's all been there. We've done some calculator now. We've spent several days earlier doing the no calculator with the trig. Okay, that's a big part of it right there. You know, on Monday we'll do a little more practice with the derivative rules and making sure we can do some of those. Really what we have left is to get into the other track just a little more with the initial conditions and some differential equation things. So let's do this next. If we'd have done that for you last night, we wouldn't have been any homework. All right. Wait, which part didn't you know last night?
I just didn't know how to use my calculator.
The calculator part. Yeah, that's true. Good point. I was going to say, because all of this was, none of this is new. Yeah, none of this is new. Okay. All right. So, I should have shown the solve menu. Oh, wait. Which part? I should have told you 44 was use your calculator. Yes, I should. All right. Because as I thought about that, I thought I forgot to tell them to use their calculator. And I know these students, and they'll sit there and they'll say, no, I'm not going to use that calculator. I know it's there, but I am not going to use it. Parker not want me. So, I felt bad. All right. So, here's what I want you to do now. Okay, this is one of our homework questions. I promise, I know that this is another screw up I had yesterday. We did number 8 yesterday, right?
Yeah.
And then I didn't even assign it as one, so I'm not, that's okay. It was worth doing. But it got us to talk about initial value problems a little bit. But this one most definitely is part of your homework. And we're going to turn back to page Turn back to page 131, and this will fit very nicely with Harry's sentiment there about, wish I didn't know this, because most years when I've assigned this problem, we come back the next day and end up doing the whole thing. So what we're going to do instead, and I had actually planned this before that discussion anyway, but we're going to go ahead and get started together on this problem. It's number 48 on page 131. Okay, and this is, I'll just write up the homework for Monday, is 8 through 14 and 48 in that section. Now you might also start looking at the chapter 2 on the assignment sheet. I've been kind of going away from the. That didn't work very good there. This is 40. Okay. On the assignment sheet at the end is some chapter 2 review stuff. It would be a pretty good idea. Think about now quiz on Tuesday. All right, and you're not going to want to just start on those on Monday night, I don't believe. Okay, so it'd be a pretty good idea to get started going through the Chapter 2 review exercises also. All right, so let's just write those up there as a, what I'm going to come around and check would be the ones in the box there. But get started on that Chapter 2 review. Okay, so 48 on section 2.5, which is on page 131, go ahead and read through that. As a matter of fact, read through the different parts of it as well. I'm going to give you about 10 minutes to get as far as you can, maybe working with a partner or whatever. If you can't do one part, skip to another part.
We're on the 48 and 2.5.
Page 131. Okay. I think that's 2.5.
It's 2.6.
It's 2.5.
Oh, never mind.
This is, I can start this one.